First off, I want to welcome everybody to our Batesville Products webinar in simulation with MAGMASoft today. We are hosting this webinar today to discuss the casting process simulation and then secrets revealed with that. First and foremost, before we get started, I want to introduce the group. But before we do that, if you do have any questions, please make sure you enter them in the questions tab. We'll make sure we try to get them answered throughout the presentation today. If there are any questions left over at the end, we will get them answered at that time. But timing permitted, if we can't get to everything, just know that we will follow up afterwards. Make sure that everybody does get their questions answered today. So with that being said, we'll go ahead and get this kicked off. I'd like to introduce our panelists today. So we have Vadim Pikovic from MAGMASoft, who is our guest speaker today. Vadim is very much into chess, and like Tim Weber, if you want to talk about bikes, he can be your guy. And he's into reading and woodworking. Trevor and Tim here have also been on these webinars before, so if you haven't met them in the past, I'd like to take a second to introduce them as well. Between the both of them, we have roughly about 60 years of permanent mold experience. As I mentioned, Tim Weber spends a lot of time on bicycles, so if you have any of those questions, you know, Vadim and Tim Weber, we may have to start a webinar based on bicycles for you guys here. And Trevor has a lot of experience here with the industry in doing anything from designing permanent molds and engineering permanent molds to now being the production manager on a permanent mold process floor as well. So with that being said, go ahead and get this kicked off and hand it over to you guys.
All right, this is good. Thanks, Tim. Thank you. If you don't know, Vadim's a superstar. I've learned a lot already, and I'm gonna let him kick it off.
Well, thank you for the introduction, Tim and Trevor. It's nice to see you on camera, and everyone else in the audience. I would have loved to see you guys in person and meet you. This is an interesting for me. I've never done this before, live on camera, kind of doing this webinar. So hopefully we don't get into too many hiccups and issues. And with that in mind, once again, thank you for the introduction. Welcome to the webinar, and let's get started. The main intent here from my side is to provide a informative, educational, and practical overview of casting process simulation technologies and the benefits associated with using the technology in the foundry, but also in the product development arena. So I'm hoping that there's casting buyers and designers out here with us today who can potentially benefit from understanding and learning more about this. So yeah, I guess there are three basic sections in this in the outline today. We'll take a very brief casting process overview, take a look at the history of simulation, and then we'll focus on casting design and process examples. There's some animation clips, some visuals that provide some insight on how technology can benefit casting process development and production. Next slide, please. Do I have the controls? Oh, here we go. Yeah. So for most of us who visit a metal casting facility, a foundry, and get a chance to observe pouring of castings, as exciting as it is, what happens, the most interesting part happens inside the black box. On the non-ferrous side of things, we see aluminum being poured, as you can see in this video. On the ferrous side, there's a lot of sparks and smoke and high temperature alloys being poured into either a sand mold or a green sand or chemically bonded sand. But as I mentioned, most interesting things happen inside the black box. And on the next slide, we can appreciate the complexity of the interaction that has taken place. Everything's taken, it's a complex interaction between the alloy, molding media, process parameters that have to be considered simultaneously. At a basic level, and I think I paused this video, so I'm going to play it again. Apologize, guys. So at a basic level, nowadays, casting simulation tools provide accurate and reliable predictions of casting quality. But foundry engineers, management, and casting buyers and designers have recognized that casting process simulation offers more far-reaching benefits. among which are the ability to develop technical knowledge database. It's a continuous improvement tool to optimize quality and cost, and it's the platform for communication with designers of castings that can use the information to optimize performance, quality, cost, and weight. Before we specifically focus on some of these benefits, let's take a brief look at the history of casting process simulation. Back in early 19th century, Fourier provided a basis for developed theoretical fundamentals of heat conduction in solid materials, and provided a basis for all following calculations of heat and mass transfer for all solid materials. Navier and Stokes provided basis for fluid dynamic calculations, and the differential equations describing fluid flow are now known as Navier-Stokes equations. And Adolf Fick in 1955 published his developments describing fusion, mathematically describing fusion processes. These and other key fundamental discoveries helped to describe the casting process in a physical mathematical models that later were solved using numerical methods. And we'll take a quick look at this timeline. This timeline gives us a glance at the major milestones in the evolution of casting process technologies, starting from 1D and 2D models developed early in the universities in the early 1970s and 80s, and progressed through various stages of development to what it is today, a powerful autonomous engineering and optimization technology.
And Vadim, cut back that slide a second, Tim. Commercially, we were talking like early 1990s is when really became available to regular folks, and I think you had to do something with the power of the computer, I'm guessing, right?
That's correct. That's correct. You know, the complex physics required a significant amount of computing power, and the theoretical models have been developed and validated on paper and in graphical form. But it's the computer development of the computer technologies that helped things back until early 80s and late 80s and early 90s, when we really started to see some of the IBMs and Silicon Graphics coming on the scene and allowing us to run complex codes and develop results that are useful and that became useful to practitioners of metal casting technologies.
Nice. Good.
Cool. That's a great question. And so basically, once again, to recap what I just described in the first opening slides, fundamental science, numerical methods, and high power computing converge to replace physical trial and error casting development with virtual experimentation and process optimizations. Over 5,000 years, metal casters persevered in advancing metal casting technologies by being patient and learning from physical trial and errors. But we would like to avoid that. In just a second, I'm going to step away from the lights back on. And with the tools being in development now and in use, we don't need to go through physical trial and error and experimentation. It's all can be done in a virtual field of experiments and process optimization. Moving on to the next slide, what I'd like to do here is to focus on some of the several practical examples of where casting process simulation has the strongest impact. Every well-developed casting goes through or should go through 4 basic development stages. We first take a look at the casting design. We need to look at the casting design and understand its castability in terms of its ability to interact with the alloy and the molding media, and how the part would react to its orientation in the mold. Once we understand the nature of the part and what it would like to do in the solidification stage, the process engineers then spend a lot of their effort to determine effective right placement of feeders and/or chills to eliminate potential internal shrink porosity that can form produce problems in terms of performance of the component. Following those two steps, design of effective metal delivery system is carried out, and fine-tuning of casting process parameters is done to optimize quality, but also optimize the process parameters to find that robust process window, which is what virtual experimentation optimization allows us to do today.
Hey, Trevor, I had a good question kind of come across here. So I want to remind everybody, if you do have any questions, make sure you insert them in the questions section, and we'll get them answered throughout this presentation. Trevor, how do you see this type of process or simulation used in the casting industry, coming from the engineering side of things?
So back when I was doing full-time design engineering, it's a very valuable tool in the fact that you can cut a lot of time down, and sometimes it extends time, but the good thing about it, it can cut costs down because you're not spending time recutting molds or redoing profiles on the CAD system is where you want to spend your time, not, removing metal or welding it back up and things like that. One of the things that I wanted to point on with Vadim is that very first bullet point of the casting design. I think in every webinar we've talked in some portion about casting design and how important that is, up front. And a lot of people understanding what is required to make a casting, the drafts, the wall thicknesses, thick sections inside of thin sections to try to get to fill out, all those important things. Once we get that driven, the other ones can fall in place. But I really think that that's one of the bigger topics, is that first one. Probably in the neighborhood of 100 to 150 over time I've been here.
And Tim, a good question came across too. So does every foundry use this type of software, or are you seeing it at specific foundries, and would you recommend it being used?
So I think Vadim could probably answer that better than myself, but I do not see all foundries using it, and I don't see it being used consistently within the foundries that do it. I see a lot of foundries that will pick and choose. They'll say, well, this looks like something we've done before, so we don't have to go through that process. But I think it's highly valuable. And just speaking from we're sitting, we do, every single mold gets a analysis like this. Vadim, what's your thoughts on that?
Yeah, that's a great point. In my perspective, every foundry should have this tool. And that has become a standard for a lot of our customers who are on the design end, and they are assessing the risks of having product failures and product recalls associated with casting quality. So on the front end, they're bringing the tools into their development activities on the front end to be able to capture the entire path of the casting, from the design table or the workstation to the tooling engineer, to the foundry, to the final use, intended use. Unfortunately, as you mentioned, not every foundry is using this for a variety of reasons, but part of it is education, part of it is resources, and part of it is potentially a complexity of the part. But in any case, today's economy dictates that we need to optimize our process so that we can take every penny off the floor to be able to be profitable and to provide our customers with best return for their investment. So that's kind of the take on that.
Yeah.
Hey Vadim, I did have a good question come across. Is the simulation customized for the casting process? So we talk about a couple different types of casting process, from die casting, sand casting, permanent mold casting. Is it customized for the different types of processes?
And I guess I'm a little bit unclear on the word customized, but I'll give an answer from my perspective, from the perspective of what we do and what type of products and technologies we offer. We cover pretty much every industrial casting process out there, starting with gravity sand casting for ferrous, non-ferrous alloys, getting into high temperature alloys, permanent mold, high pressure die casting, investment casting. So And with that, yes, there is a degree of customization. It's not one solver fits all. It's not one solution fits all. A big part of it is the capabilities of the software and the thermophysical data sets that come with each solver or module, as we call it. And so that's part of the answer, I guess.
Great, thanks.
All right, so Trevor touched up on the. I wanted to piggyback on something what he said about the need to talk about design of the part, and what I thought of as concurrent engineering, being able to bring designers and the foundry process engineers to that table initially while the part is being quoted, and the economics of the process and the part are being studied by the supply chain and salespeople. And ultimately, the goal is to provide a common communication platform so that we bring the language from the foundry and bring the language that the designers speak and combine them all in one simple to understand set of results or solutions. So this is what I would like to talk about here at this point in the next several slides. And the example I'm using is a fairly simple A356 cast aluminum cast arm. It weighs about 3 pounds, just over 3 pounds, and I've given just the major dimensions so you kind of get an idea of the scale of the part. It's cored. There's a sand core inside the hollow volume of the part, and it's made in a permanent mold process. So once again, I mentioned the first step in the process to look at the castability, what's called castability or solidification characteristics. And what you're seeing on the left side is an animation clip. It's a solidification sequence that shows the conversion of transition of metal from liquid to solid. And anything that's transparent already has solidified and cannot be fed. And anything that's still in some sort of a color scale, you can see in that animation is still either fully liquid or some mushy metal. And so how is this information is used? Well, number one, the designer, if he sees this, he can understand the balance between thin to thick sections, and potentially can take steps in reducing some of these transitions or contrast, and to be able to more uniformly solidify the part. The process engineer in the foundry is looking at the hotspots and thermal centers and trying to figure out the best way to locate feeders and size them properly so they can take care of the isolated volumes that are left in the part to draw that shrink, potential volumetric shrink that will occur in a part. Furthermore, additional results, so kind of moving beyond solidification analysis that's been used for the next couple of decades. There's tremendous amount of power in utilizing other results that are available, such as microstructure and property predictions. And I'll talk about in my next slide, but what you're seeing on the right is predicted shrink porosity locations circled, specifically the ones that are opened up during machining and may present issues in terms of performance and overall quality of the part. So the goal is to once again, is to understand these risks and be able to address them early in the design stage and communicate with the foundry in order to be able to set acceptable and reasonable quality acceptance criteria.
Hey, Tim, had a good question come across from Mark here, and I think we've talked about it in some previous webinars, but not necessarily on the one today. So often either the mold builder or the foundry isn't chosen during the design process of the part. So how would somebody manufacturing the part like you work with that customer or the design that is presented at that time?
That's a great question. And today I'll use the term cross-functional teams that are implemented so that designers don't design anything in a complete vacuum by just looking at structural mechanics and other disciplines that go into developing a functional component. So early in the design stage, there's a material selection process that the designers should go through in conjunction with their purchasing and supplier quality groups in order to understand the best DFM capability of the part and what needs to be done. In other words, can this part be cast in sand, or does it need to be produced in permanent mold? And knowing a little bit about heat transfer and physics and material science, we know that sand may be giving us a part with lower mechanical properties, which I'll talk about in the next slide, versus permanent mold, which is what the designer may be looking for. So in the software itself, there's a number of opportunities to do a what-if analysis very quickly by interchanging molding media, for example, and some of the basic process parameters without really knowing every nuts and bolts of the foundry business and technology, to be able to get a qualitative and furthermore quantitative understanding of how the part will react to the process.
Great, thanks. Hey, Tim, a good question came across. So should this, or do you see this software being used for troubleshooting after the original tool has been completed?
Oh, for sure. From just experience that we've had here, we've had engineers bring us product that they were having issues with and couldn't get it resolved at their current supplier. So they would bring the part to us, and we pretty much troubleshoot it this way. I think, Trevor, there's a few that I think come to mind where they were having a significant amount of rejects, and we ran a simulation, and man, it was real obvious what was going on. And a lot of it even has to do with what Vadim talked about, and we'll talk about later. It's just, the mechanics of the mold. This thing has to be able to be producible. You're not making just one, you're making multiple. So, we got to make sure that, managing the heat, that's critical. That's just critical.
Vadim, before we get off the slide, Sadir had asked a question. What is the, let's make sure I'm pronouncing this correctly, the Nehemiah criterion there?
I'm sorry, can you repeat the question, please?
So on that slide there, it says at the bottom, Nehemiah criterion.
Oh, Niyama criterion, that's a great question, and I'm glad you guys asked me. It's a thermal criterion that looks at the relationship between the cooling rates and thermal gradients, and it's very well published and established and published in the literature. And the criterion is specific to a set of alloys. In this case, it's unique to alloy groups that are solidifying in a dendritic fashion with longer freezing ranges, which what aluminums and steels would do. It's widely used for steels. There's some use of Niyama criterion for copper-based alloys as well as aluminum. In this case, it's A356. So the scale that's shown with the lower values of Niyama criterion, we're seeing highly isolated formations of shrink pores that need to be addressed by either changing the design, changing the thermal criteria conditions in the mold, and or moving feeding aids.
Great, thank you.
So Tim, going back to your question, I think what I got from what you were saying was on the design side, how soon should you get into the design of, first of all, yeah, you got to determine it's going to be a casting. But as soon as you determine that casting needs to be made that way, I think it's a good beneficial time frame to start looking at design with some other people that are experts in the area. If I was to throw that out, don't you agree? Tim?
Yeah, you can't get the foundry and the engineers involved too early, in my mind. As soon as you,
it's better for everything.
Yeah,
all the way around.
All the way around. And this is all we do. This is all Vadim does. And a lot of times it's not that engineers aren't just drawing up castings all day long.
Right.
So ask that question up front, and and start looking at some of the technology that's available. Using it.
Especially when you're looking at multiple assembly components that are being designed. There may be 2 or 3 that are great for castings and the other ones aren't. So that's kind of what I want to point out there.
Okay, well, on to the next slide, and I mentioned once again, in the context of concurrent design, what else can a design engineer learn from the interaction with the foundry, and using that platform, that casting process simulation platform? Well, there's an opportunity to predict mechanical property. Microstructure and mechanical properties can be directly evaluated, brought back into the design phase. On the left side, you see a plot of predicted secondary dendrite arm spacing as a function of the alloy and cooling thermal conditions within the system or the mold. And we know that SDAS is closely related to the fatigue strength of the part. And so it's very important to be able to, in safety critical components that undergo cyclic loading, be able to understand the distribution of secondary dendrite arm spacing, which has been a standard in the automotive industry. On the right side, you see a plot of predicted mechanical yield strength in a standard T6 condition. So essentially, what the casting has done is has been through is solidification and cooling, and then a standard T6 treatment. And you can see a variation in mechanical properties. Although the spread is not tremendously large, this serves as an illustration of the opportunity to understand what those differences may be, and then bring it back into the design phase and compare them with say finite element structural analysis to understand what the risks may be in certain areas, whether the part is going to live through those stresses and strains or not. And once again, it goes back to the point about communication with the designers and the value that the software can provide to the design community.
So, Vadim, we talked about this earlier, but so this is showing you different mechanical properties throughout that cast part. Does that same type of situation also exist in an extruded part?
While the mechanical working, the direction in which the mechanical deformations are applied are certainly going to produce non-uniform properties throughout the part. So the distribution there may be more predictable and controlled in the sense of knowing that we're starting out with an ingot and then working it in a very controlled situation or environment. But again, that is also important. Extrusions, stampings, forgings, there's a slew of simulation packages that exist that provide a tremendous amount of information to the designers as to the strength and durability of their components. So it's critical to look at those processes as well, and not assume that your properties are homogeneous throughout the part.
That's a good point. Yep.
Okay, jumping on to the next slide. This is sort of an extension of what I was talking about before. In a traditional design process, the conventional design methods do not consider the impact of microstructure, internal shrink, and residual stresses on the performance, the strength and durability of the component. And casting, the established techniques assume homogeneous properties throughout the entire part, and as a result, only one data set of material data set is used in the analysis. So that's kind of the illustration on the left side of this slide. This is sort of the conventional way of doing things right now. With casting process simulation, using these results that I just talked about previously, there is an ability to link casting process design and casting process, link it with the predictive analysis in the production development stage in order to evaluate the durability and the strength of the component. And this has a tremendous impact on being able to utilize the full potential of the material, optimize the performance, optimize weight, and meet those ever stringent lightweight requirements that are being driven down the design through the design community. So that was something that we talked about in terms of how casting process simulation, what type of role it plays in the casting process design, and now we're ahead of a casting process engineer in a foundry and look look through his lenses and understand what he can do with these tools and what type of benefits are there. On the left side, there's a cross-sectional view of that cast arm with a feeder or a riser, as we call it, attached to the heavy section of the part, and you can see that there is a micro shrink that's extending through the wall and closer to the riser, and so and once that feature is machined on the inside, that shrink is going to be amplified visually and may cause issues, for the performance of the component. So the goal is to optimize the location and size of the feeder to drive that micro shrink away from the outside machine surface once the riser is removed. And so optimization provides that powerful tool, powerful opportunity to look at a wider design space in a very short amount of time. What you're seeing in that animation in the center portion of the screen are the combinations of the two feeders, their sizes that are being cycled through. We're stepping through about 80 designs here in about 4 to 5 hours with the objectives of reducing yield, or optimizing yield, casting yield, reducing hotspots, and then reducing the average microporosity. So as a result, on the right side, that screenshot you're seeing, that micro shrink is still in the part, but it's further away from the functional areas that are of the concern to the design engineers. And the scatter charts up on top in the right corner provide correlation between the height and the diameter of each riser and the average microporosity. So once again, we're not just considering one design or going in a serial way of changing physically or manually changing the size of the riser. We're plugging in a large number of reasonable casting riser designs and trying to figure out which combination of the two will give us lowest micro shrink with the optimal casting yield. So that's really the power of using this tool on a front end before the tools are cut and physical sampling in the foundry begins.
Hey Trevor, a good question came across. So when in your designing expertise that you had in the past and your current production side of things, how do you look at roughly estimate the ratio between the part weight and the material quantity for feeding the channels, risers, gates, part? How do you estimate that? How do you build that into your design?
Well, it's all kind of based upon the design of the part, Tim, to be honest with you. If like he's doing there's multiple different yields that you can get through that animation he was doing, but there's certain things that you just can't get away from, and thick sections are one of those. If I was to just throw out a rule of thumb, probably looking at part weight times 2. I mean, it's not always double type of thing, but that's why, in this simulation here, he's showing that, you can optimize that yield on your casting. So it may not necessarily be 2, it may be 1.5 times, so that's a lot better for everybody in the long run.
And that's what he's doing here. And I think he's running through the 80 different variations to see what is optimal. Just to reiterate, what the first 2 slides were that part is in space, liquidus at temperature, at liquidus temperature, and then Vadim's software just lets it go in space and set up and cool. Okay, that shows us we've got hot spots, we've got some areas that could cause problems. This is the remedy. This is the software looking at remedies. And what's the best remedy? Where is it going to give us the best results with the least amount of material and cost? Like not just material cost, but time cost. If you got a big riser, you got to wait till it sets up.
Right.
Yeah, it slows your processing down. So this optimizing, I love this. I think this is a great slide.
Yeah, I just wanted to add one more little facet to this discussion, and then just to be more accurate, the part is surrounded by a mold,
Right.
whether it's sand or permanent mold. We're not filling the part. We're not bringing the metal in as we would to a gating system, but we're allowing, like you said correctly, we're allowing it to solidify from fully liquid state to solid and cool down to ambient if we have to. What I wanted to mention too on this slide is regarding your question, Tim, about what are the rules of thumb and what are the methods are used to calculate the size of feeders. Korenov, one of the fundamental researchers and developers of some of these rules, early on relayed them he developed this criterion called section modulus or feeding modulus, and he looked at it from perspective of volume over surface area. But the problem, unfortunately, it's a little bit of an overestimation because it does not include the thermophysical properties of the interaction between the alloy and the molding media. And so in this sense, the software allows you for a much more accurate capture of that interaction. And so you're optimizing your feeders not only on using the size of the part and the surface area, but also accounting for the alloy properties and the sand mold or the molding media material properties. So, but that's a great question. We use a result called feeding modulus, in other words. And so we look at the value of the major feeding modulus in the part, and then we backward calculate a starting point for some of these feeders, and then move it right into the optimization phase.
Great, thank you.
All right, let's move on to the next step. I think this is going to be a little bit more exciting because we're looking at a fluid flow problem. We're filling the mold with liquid aluminum, and again, I wanted to emphasize that the term here is casting process simulation. It's not just solidification modeling that's been thrown around in the industry or used in the industry in different ways, or mold flow or flow modeling. It's trying to capture the entire metal casting process from bringing the metal into the mold, allowing it to solidify, and then allowing it to cool to room temperature. And so what you're seeing on the left side is a temperature scale. It's a metal temperature animation. In other words, we're tracking metal temperatures throughout the system in a scale of starting pouring temperature of 1375 Fahrenheit to the liquidus point. And liquidus point is where we see metal turning into solid. And so one of the challenges with this particular part or a design at this point, visually you see that there's a volume of cold metal forming up at the top of the part. And depending on the process conditions and the amount of variability, this could result in metal falling below the liquidus or reaching the liquidus. And then we have a problem of an issue of forming cold laps or non-fills. So this is something that we're going to focus on in the next couple slides. The animation on the right side is what we call a tracer particle result. It allows us to look and take an X-ray view into the metal stream and understand the various eddies and direction in which the metal flows throughout the part. So let's take a closer look on the next slide. There's a static image of one of the steps in that sequence.
Hey, before we do, Tim Weber, are you able to simulate dimensional accuracy from specified tolerances and or surface finish expected? So do you see that used a lot? Sadir had asked this question. Do you see that used a lot for those types of specifications on prints or drawings?
Jeff, I'll let you handle that one.
Dimensional accuracy, of course, the part's going to shrink. So there's a rule of thumb, 7 thousandths per inch type of rule that we typically try to build into that. On the surface finish, I think that's all kind of comparative to, it can have stuff to do with the turbulence for sure, but it's all kind of comparative to the mold itself, the structure that's around the part that you're trying to pour. So there are different types of coatings, different types of sands, different types of uses for these coatings that create different types of surface finish. So, I wouldn't see this as being a means of predicting surface finish for sure, but you could get into the means of predicting the possible dimensionals.
All right, thank you.
To piggyback just real quick on the previous slide, to piggyback on that comment. You know, as a final step, you see a thermal distribution of differences in temperature throughout the part, and that will lead to differences in volumetric contraction as the part starts to cool. And depending on how the strains and stresses are acting on the part throughout that process, we may see some issues with part distorting outside of the normal nominal conditions or dimensions. So that is the power of the simulation technology, to be able to capture those thermal fields and bring that into a thermal stress analysis arena in order to be able to get a feel for how far off we may be with the final shape of the part, and or if there are any other issues with the structural integrity and or residual stresses. But going back to my discussion about the flow through the system, on the left side is a static image of you know, a step in that process. And I was hoping maybe in the audience somebody could point out to some of the challenges that we're seeing there, what they are, and maybe I'll give the audience a second or two to raise a hand and say, yeah, I know what's going on here. But I'll continue to talk as we see the path of the particles, tracer particles coming through the lower gate. We also have a gate on the left side at 9 o'clock position, and then there's a gate at 10 o'clock position and 11 o'clock position, and going all the way up to the top. Yeah. But the prevalent flow of metal is through the casting through the lower gate, and what we're seeing the metal flowing out of the casting at some point through the other gates. And that is effectively demonstrated by capturing the mass flow curves through these in gates. For those of you who may be confused by overwhelmed by the amount of detail on the slide, I'll explain. In the center, you see a casting with numbers 1, 2, 3, 4, 5, and 6. Those numbers are IDs for each individual in gate. And on the right side, upper right corner in that graph, those gates are referenced by colors. So gate 1 is the one that you're seeing peaking and then coming down a little bit and continuing to produce positive metal flow. In other words, casting flowing the metal is flowing through the casting, as opposed to the other gates being activated at some point, but then at some point, at other points in time, metal flowing out of the casting through those in gates. And that is a less desirable condition, because we can incur some issues with the metal contamination, inclusions, oxides, and or just generally speaking, a high amount of turbulence. But more importantly, we're looking at a thermal problem with cold metal up at the top. And that occurs because the casting is not filling fast enough. And again, it's not filling fast enough because we're not putting all that metal into the casting. We're flowing some of it back into the runner. So that's the power of some of these results, to being visually, not only visually, but quantitatively describe potential issues with the setup, and be able to then come up with a root cause analysis and remedy to solutions. So here we have a comparison between 3 different designs. On the left side, there's an initial design with 6 in gates. Then there's in the middle, there's a design with 4 in gates. And finally, on the right side, we removed all the other in gates and just left the 2 at the bottom. And we're tracking metal temperatures again in terms of the scale of initial to liquidus. And you can appreciate, even qualitatively, just but not even looking at the scale, that design on the right side is keeping the metal hot enough where we don't even get close to the liquidus point. So that is a positive indicator of improvement in the process. And so we can look at potential changes to the tooling in terms of changing the runner design to be able to bring the metal in quicker, more effectively, without jeopardizing the quality of the part. And that is also supported, interestingly enough, by the result that shows the evolution of the displacement of air by the metal. And I'll explain that this may be a little bit confusing to you guys. Anything that's transparent in these images and animations is already filled with metal. Anything in blue or other colors is still air in a system. And what's important to track is the amount, the uniformity of how the air is being displaced by the metal, and kind of visually comparing where that last region of air ends up in the casting. And you can see that by changing the upper design of the runner in the upper portion of the casting, there's a single point of venting, and effectively we're evacuating air without potentially trapping it in the casting. Again, this image here shows a static, this slide shows a comparison between static images at the same sequence step. And you can see that the design on the left with the 6-gate configuration shows a risk of trapping air in the upmost portion of the casting, as opposed to gradually evacuating that air completely from the casting through the upper feeder. And that upper feeder also provides us with an opportunity to feed the casting effectively by replacing that runner geometry in the original design. So just kind of that was my objective of producing some visuals to demonstrate some of the practical applications of casting process simulation, some of the thought process and logic behind understanding what these results mean, and taking maybe the next step above and beyond, and figuring out what to do with them. What are the things we can improve in the design, either of the casting or in the design of the rigging system. And I'm going to conclude this discussion with this slide, this powerful slide showing the opportunity to save by modifying the runner and removing about 4 pounds of metal. There's an opportunity to save $4.56 per part. So that's to the point that casting process simulation is a powerful business tool. It's a tool for the foundry to be able to optimize their process and optimize their cost and increase revenue. So
when I see this slide, also I look at the image on the right hand side. When I look at that, that tells me that part's going to run faster than the part on the left. So not only going to save $1.14 a pound, you're going to process a heck of a lot more castings with the proper gate and rise ring. I think this is a great. The last 3 slides, we show what the problem is, we show some some opportunity, and then here's the dollar and cents. Here's where the rubber hits the road, and it's a better part and it's a cheaper part.
Yeah, that's a fantastic catch, Tim. Not only you're reducing the amount of metal, the till time is faster, and the cleaning costs are lower too. So exactly. With that in mind, I wanted to just wrap up this discussion by quickly summarizing, just generally speaking, effective uses of simulation. Obviously, predictive capabilities are very powerful. Looking at current jobs and looking at optimizing either tooling design, reducing scrap rate, improving quality. Well, I'm sorry, I meant that by saying diagnostic, looking at simulating reality to look inside the black box, and those are the powerful benefits. But also predictive, we talked about bringing that into the design stage and looking at concurrent engineering. I mentioned education of the workforce, education of customers, education of anybody who deals with castings, and research and development. Those are the 4 arenas where we see tremendous value in using casting process simulation.
A big part of that education thing also, I believe, is just being transparent with your customer and sharing that information with them. I think there's as a marketing guy, a sales guy, I think there's a play that way, but just getting those your customers involved and showing them the opportunities, I think is a big deal. I think there's a lot of upside there.
All right,
yeah, I wanted to thank you.
We will go ahead and pose if there's any additional questions. I am getting quite a bit of questions here. Some are fairly specific. So I want to make sure that everybody knows as we end here that we will make sure we get those questions answered offline if we haven't answered them on the webinar here yet. And I did want to make everybody aware we do have a webinar coming up here in the beginning of March, on March 9th. If you have time available, we'd be happy to have you join us. We'll be discussing the 5 critical elements to be considered when machining aluminum castings. So taking it a step further just from the casting perspective, and some items to look for when you're machining them. At this time, I would like to thank Vadim, Tim Weber, and Trevor Bovard for your guys' time today. We will, again, make sure that we answer all these questions offline here as we come to a close. But thank you guys for your time today, and I appreciate everybody taking time out of their busy day to attend.
All right, thank you.
Thank you.
Thank you, guys, and thank everyone in the audience. Thank you.
Okay.